Coding agent wrote the logic for the famous WhatsApp delivery ticks in 3 seconds. Single tick sent, double tick delivered, blue tick read. So what exactly is your job? Now here is what AI did not do. Realize that if you use the user's phone clock to order those messages, the network latency will cause replies to arrive before the original questions. AI trusts the device. You design a monotonic sequence generator on the server to guarantee absolute unbreakable order. That judgment call is the one that keeps group chats from becoming an unintelligible mess. After this video, you will be able to make it and explain exactly why that is the skill that survives. 5 things you will own after this video. Why relying on mobile phone clocks causes messages to time travel. The exact architecture of a monotonic sequence generator using Snowflake IDs, the specific network hops for all 3 WhatsApp ticks, send, delivered, and read. The trade-off AI misses when asked to design this, and the survival skill mistrusting the client. If you watch this video to the end, you'll be able to answer a message ordering interview question better than 99% of candidates who have been building software for years. Let us start with what breaks. Imagine user A asks a question and user B answers it immediately. If we use the timestamp from their phones to sort the chat, what happens if user A's clock is 5 seconds fast? User A sends hello stamped at 10:00:05. User B receives it and instantly replies hi, but user B's clock is slow. The reply is stamped at 10:00:02. When the database sorts the chat by timestamp, user B's reply appears 3 seconds before user A's question. The chat history is permanently corrupted. This is the time travel trap. The client timestamp approach breaks at WhatsApp scale immediately because you cannot trust 2 billion mobile phone clocks to be synchronized perfectly. This is the problem that forces a centralized sequence architecture. Not because timestamps are bad, because the distributed clock drift constraint makes local time physically untrustworthy. That constraint is the entire reason for everything that comes next. Instead of trusting the customer's watch, imagine a busy bakery. When you walk in, you pull a numbered ticket from a central dispenser. Ticket 5, then ticket 6. It does not matter what time your watch is. Ticket 6 always comes after ticket 5. That is a monotonic sequence generator. It is a system that guarantees the next number it issues is strictly greater than the last one, regardless of time. WhatsApp uses these sequence IDs to sort messages, completely ignoring the time on your phone. At WhatsApp scale, a single ticket dispenser would become a bottleneck, so they use distributed sequence generators, similar to Twitter Snowflake. A Snowflake ID is a 64-bit integer. The first 41 bits are the server's time. The next 10 bits identify the specific worker machine, and the last 12 bits are a sequence number. Because the server time comes first, the IDs are naturally sortable. Because of the worker and sequence bits, two servers can never generate the exact same ID, even at the exact same millisecond. Every architecture trades one thing for another. A monotonic sequence generator requires dedicated infrastructure like Zookeeper to manage the worker IDs and prevent collisions. It forces clients to depend on the server for order. But WhatsApp cannot afford out-of-order messages. The cost of maintaining the sequence generator is trivial compared to the chaos of corrupted chat histories. That is the constraint-based reasoning that separates a developer from an engineer. The developer uses Date.now, the engineer provisions a Snowflake cluster. Now, how does WhatsApp actually wire this up with the famous check marks? Let us look at the flow. The WhatsApp backend coordinates 3 distinct acknowledgement messages or ACKs to render those ticks on your screen. Let us trace the exact hops. User A sends a message. It hits the chat server. The chat server immediately pulls a monotonic sequence ID. It stamps the message. This guarantees its order permanently. The server sends an ACK back to user A. The app renders a single gray tick. This tick means the server has the message and it is safely stamped. The server routes the message to user B's open WebSocket connection. The moment user B's phone downloads the payload, even if the screen is locked, the app sends a client ACK back to the server. The server forwards this ACK to user A. The app renders a double gray tick. This tick means the payload is on their device. Finally, user B opens the chat window. The UI triggers a read ACK back to the server. The server forwards the read ACK to user A. The app renders the double blue ticks. Three separate asynchronous flows, all tied together by that single monotonic sequence ID. If this kind of judgment call, breaking down a simple UI feature into a strict distributed systems problem, is what you want to make confidently, subscribe now. Every Tuesday, one system design judgment call free. Network time protocol is imperfect on mobile networks. Phones drift by seconds or even minutes. A monotonic sequence is strictly server controlled. It is completely immune to mobile clock manipulation. With client time, a reply can be stamped earlier than the question, corrupting the chat history forever. With a sequence ID, the guarantee is absolute. ID 6 always comes after ID 5, regardless of network lag. Ask an AI to implement chat sorting and it generates Date.now, logically correct on one machine, a complete failure globally. The engineer defaults to the constraint. The answer is not use a sequence ID because it is safer. The answer is the physical reality of clock drift across 2 billion mobile devices makes local timestamps impossible. That answer is the one that gets you hired. Let us put it all together one final time. The full system in one clean view. Full system, every component visible. Here is the complete journey of a message and its three ticks. User A sends a message tagged with the local temporary UUID. The chat server requests a monotonic sequence ID, mapping it to the local UUID to establish global order. The server ACK flows back. User A sees a single tick. The payload is pushed to user B. User B's device silently confirms receipt. The server forwards this ACK to user A, double tick rendered. User B opens the app. The read ACK fires. The server forwards the read ACK. Blue ticks rendered 8 asynchronous hops, perfectly ordered by one sequence generator. Before this video, the answer to how does WhatsApp sort messages was they use timestamps. After this video, the answer is clock drift makes local time untrustworthy. WhatsApp uses a centralized monotonic sequence generator like Snowflake to guarantee absolute causal order and manages delivery state via three distinct asynchronous acts. That shift is the judgment call that no AI prompt can generate. That shift is your job. You now own the architecture. Last piece. How do you walk an interviewer through this in 45 minutes? That is next. 45 minutes, blank whiteboard. Phase 1 is clarifying constraints. Ask the interviewer, are we guaranteeing exact causal order? Are we assuming mobile devices have severe clock drift? Phase 2. Propose the naive approach. Say out loud that relying on Date.now on the client will cause messages to time travel and corrupt the chat history. Prove you know why it fails. Phase 3. Introduce the solution. Explain Twitter, Snowflake, or a similar 64-bit ID generator that combines server time with a worker ID to create sortable collision-free numbers. Phase 4. Delivery state. The interviewer will ask how the ticks work. Break it down into the three distinct arcs: server ACK, client ACK, and read ACK. Explain that they are completely decoupled from the message payload itself. Finally, phase 5, the trade-offs. Acknowledge that a centralized sequence generator creates a single point of failure, but explain that running it in a highly available cluster like Zookeeper is mandatory to prevent out-of-order delivery. Before this video, sort by timestamp. After this video, the physical reality of clock drift across 2 billion mobile devices makes local timestamps impossible. Snowflake IDs and asynchronous arcs are the only structures that fit. The engineer who can say that in an interview, in a system design discussion, in a code review, that engineer is the one who built the system. Everyone else wrote the UI code for the blue ticks after the decision was made. That distinction is your survival skill. Next Tuesday, end-to-end encryption, the famous signal protocol. How do you encrypt a message so perfectly that not even the WhatsApp database engineers can read it. The AI default uses standard TLS, which secures the pipe but leaves the data exposed on the server. An engineer uses public key cryptography to lock the data before it ever leaves the phone. That is episode 3, the architecture that guarantees absolute privacy. Subscribe to ByteLearn for the complete One Engineer System WhatsApp edition. One system design constraint per week every Tuesday. Hit the bell. See you Tuesday. Question: which architecture judgment surprised you most? The time travel trap? Drop it below. I reply to the first 10.